My first time to KSCP, wonderful. I did spend some time at UC Santa Cruz in Berkeley when I was an undergraduate, but coming back to this area here and then really seeing the coastline, everything is really fantastic. So thank you for organizing this here. So yesterday was my first day here. I was really blown away by all the observations that we heard about, being able to test all this with real observations. Now it's time I will take you into the fog again of just theoretical, speculations. And when I started working on binary black hole mergers, now almost 10 years ago, approximately the same, time as Kyle and others, we were thinking about eccentricity, and there was a lot of people saying, all this, these outliers, it's weird stuff, it's waste of time, why are you doing it, and stuff like that. And I can happily say that now I have moved on to other strange things that people also are starting to say, well, this is some weird ideas, and we will never be able to see those kind of things. But this is where I like to work, and a lot of the groups that the group that I have now here at the Niels Bohr Institute is really, the hard work of many of these students here. So we organize a lot of meetings. I will, in the end of the talk here, advertise a new PhD school that is also coming up in Norway. And I also know that many of you have been to some of our meetings in Copenhagen here, so thank you for that. But the big question that keeps me awake during the night if I'm not just jet lagged. Now it's easy to say that I didn't sleep all night because I was reading papers. It's just because I was very jet lagged, but I did in fact stay up very late. But what we are trying to understand is where and how do binary black holes form and merge in our universe. And you can think, well, you have the measures of mass, and you have the measures of spin, and you have clusters that will give, isotropic spin distributions, and there might be something with the mass ratios you can figure out. But honestly, after the first, 100 or 200 binary black hole mergers, I think we still have no idea, where the binary black holes are coming from, right? So a lot of the ways I'm thinking is trying to pick out key observables that will tell us essentially from individual sources where the binary black holes are coming from. If we are going to eccentricity, I will talk a little bit about that, like some of the earlier works. Of course, eccentricity will point towards a dynamical formation. So at least we can isolate if we start to see these eccentric mergers that maybe dynamics plays a role. But once you open, the box of dynamical systems, you have AGN channels, you have triples, you have clusters of different masses, you have open clusters, new clusters, and there's a lot of interesting things that might happen, right? So even within that framework or within those classes, you still want to understand where does the binary black holes come from. And during this talk here, I will take you through a lot of different new ideas that we are thinking about, and I'm thinking this is the perfect place to do that because I will be spending a lot of time with many of you here, so I hope you can come up and discuss possible projects that we can work on later. So this will be a potpourri of different things that we are thinking about. Right, you can, for example, see up here at the screen here. Here I have put out, a little bit of different possible formation environments, clusters, and around supermassive black holes, or you can have like these triples. And depending on what kind of environment that the black holes are forming in, you will basically have imprints in the gravitational wave signal. And a lot of my talk will be on exactly what kind of imprints. You can naively think that if you have gas around, the gas will impact, the orbital evolution by, having gas drag or implying gas drag on the object. So the inspiral, or maybe I should get my chances for this one here. So the inspiral time relative to the frequency evolution will be different, right? So that is, of course, one of the measures. But I will be talking about things that are not so speculative. Let me see if I can get the. Oh, I didn't get the. Okay. I'll just keep pushing so I make sure that it doesn't go out here. Right. So the standard measures is that you are comparing, say, for example, the cluster channels with the binary evolution channel, and the general classes that you can split it into will be that in the dynamical channel you might have these highly centric mergers. Maybe they're more circular, certainly more circular in the binary evolution channel. There could be differences in the mass ratio, right? So if you have black holes that are interacting in clusters, you tend to go towards the more or less equal mass case just because of these frequent exchanges where you don't have the same requirements for the binary evolution channel. And the spin, as I measured, there are hints that well, definitely from the clusters, because you have many of these interactions here. You will have randomized spin distributions where for the field channel now it's very idealized here, but there will certainly be some correlation. Right? So what are the observational hints right now? So when we are talking about things that are borderline new physics, new observations, then of course there is a lot of discussion on, is that actually what we are looking at, right? So you can take the example of 1905-21, this heavy binary black hole merger. We only saw a few cycles. Clearly it was very massive, but people started to look at the eccentricity of the source. People start to look at, different higher order modes and so forth. But if you only have a few cycles, then it's very easy to fit many different models to it, right? But here, this plot here shows a compilation of Isabelle Ramirez-Shaw, which really have pioneered a lot of, at least pushing the work for looking for eccentricity. And the y-axis here shows some kind of measure of the eccentricity. Right. You can see that there's a few events that sticks out. And there was a recent event that we are looking at in particular. And this is this Trentio 208, you see it up here, and this is the paper that we put out here maybe a month ago. And this was a source that was picked out both by her team and by some other teams. Gupta, he has been doing a lot of work from the Max Planck Institute. And they have some different candidates for the eccentric sources, and one of them were like an overlapping candidate, so we took a look at that in more detail. Now you can see this here is the best fit for the eccentricity at 10 Hertz. And you can see that you don't get the same eccentricity just because you have different priors. And the reason why you have that is that the models that they're using, the different waveform models, cannot go to the same eccentricity. So Gupta's model here are able, they're better calibrated to NR simulation, that you can go to higher eccentricities, and why that is why you have this cut here. So for this kind of system here, you can then go in and ask, well, what is the likely environment that this one here could have lived in, right? So we can already do some work on that without even assuming anything about the environment. We can, for example, say, is that weird? Okay, so this source here had an eccentricity about 0.4. Is that an outlier? Is it weird that it's 0.4, not 0.1, right? So if we think about how binary black holes, they, are able to form and pair up, it is basically due to, chance encounters of, statistical, random interactions very, very close to a pericenter. And that's the same for triples and globular clusters. If you want things with high eccentricity, there's nothing fine-tuned in the problem. Things are being scattered more or less randomly very close to pericenter, right? And that is what we find basically in all different dynamical channels. And you can, from that, you can then ask, is the 0.4 an outlier? Okay, so this here shows the eccentricity at 10 Hertz, and here I have normalized to 0.4. And then here, if you, for example, look at the dashed line, like the red line here, the red lines here show what is the number of eccentric mergers that we should have expected to see at lower frequencies. With a lower eccentricity. So if we, for example, say up here that this, the number of eccentric mergers with an eccentricity greater than 0.1, right, we should have expected to see maybe a factor of 2 or 3 more compared to the one we already saw at 0.4. So that's kind of consistent with just being able to see a few. And we can also do it for the, we can say, well, it's a difference between having the scatterings happening in an isotropic in the environment, say, for example, AGN disk, where you are dominated by this, or you can take the disk limit or 2D limit of your scatterings, compared to the isotropic 3D distributions that you find in clusters. Like the two limits are, differed by that the probability of having an encounter within pericenter distance r in the 2D case goes as square root r, where in the 3D cases goes as proportional to r. Okay, so I can also go in and look at this one here, and there seems not to be a lot of difference here. I think the only constraint really comes when you're going to high eccentricities here, then you start to say, like, if we actually saw one source at 0.9 in eccentricity, maybe we should have seen a few more of 0.1 in eccentricity if any of these models here would be the underlying, right? So there are some things that we can do by just looking at the relative number. Of course, I don't have the selection effects here, but that's one thing. We did find that like a similar source here could define, conform in one of the globular clusters that Kyle will talk about later. Another thing that came out very recently, which also has been highly debated, and there are many issues with this work here, but it is at least a push forward, is a possible measure of an acceleration of a binary black hole. And the acceleration that you see here can be, basically encoded in the gravitational waveform as a function of time. I'm going to show you that in a moment here. So what they're basically saying or claiming here is that one of the binary black hole mergers that LIGO have seen does show some line of sight acceleration, indicating that it might be orbiting around either supermassive black hole or stellar mass companion. That will, of course, would be, the first direct, probe of something that is happening. Can directly tell us where these binary black holes are coming from. So to take you through a little bit here, right? So if you have, so we will go through this a few times here during the talk here. But if you have a binary black hole up here that is moving on a curved orbit here, then you will be able to measure a shift in the gravitational waveform, which is different from just the linear Doppler shift. And like many of you know, of course, you cannot measure that. It just goes as 1 plus v over c in terms of the masses, and you cannot do that, right? So you have the, you can think about the mass measurement here will be the source measurement 1 plus the cosmological, 1 plus c Doppler, which is v over c. And then you have this extra term here, which tells you about the velocity change as a function of time, right? And this one here factors in a way that does not or cannot be mimicked by just changing the masses. So the idea here is that if the binary black hole merge on a curved or moving and eventually merge on a curved orbit here, if you're sitting out here as an observer, you will see a time-changing time lag between the unperturbed and the perturbed orbit, right? And if I tele-expand here the trajectory or the deviation from this unperturbed here, I can calculate my time lag here as a function of time going as a half a t squared 1/6 a dot t third and so forth. So if I go in and measure this time lag here, I can basically go in, okay, so this is a continuation of this figure here. I can go in and measure the acceleration. Basically, I can measure a combination of the mass and the distance squared to the source, right? So if I sit down here as an observer, I have my unperturbed and a perturbed orbit here. My signal will be displaced by a factor delta t, which will correspond more or less to this light travel distance, right? Does not only hold for circular orbits, it can hold for any accelerated path here, right? So, but it is a very, very tricky measurement, and I think it's very still debatable if that's actually what has been measured in this signal. But it is something that we are starting to look at, and I'll come back to this one here. But what about the environment, right? The point is that you cannot measure m over r squared independently using this, and you also have inclination effects. So you have, sine of orbits, and you have, and like another angle that's telling you where the binary is on that orbit. Right. So let's try to go back a little bit, trying to understand where some of these sources could actually form. Right. So this is just a generic study that people have been doing. It's very easy to look for the line of sight accelerations. But now let us take a look at some, how these things can actually form in the real astrophysical environments. All right. So what you're seeing here is an evolution of a triple system inside a cluster, and Kylie will talk about that later. So the main mechanism of forming binary black holes inside clusters are these frequent interactions that you're having. And the frequent interactions are usually between black holes and other black holes, at least when you're talking about the very strong dynamics that you have in the center. And in this simulation here, I included the post-Newtonian term, and the first radiative term. The radiative term here will take energy out of the system if the objects get close enough or moving fast enough. And you can see here that the third object perturbs the binary here to such a high centricity that it basically merges while it's still bound to the third object here. Let's try to explore these a little bit more. So I'll come back to what the signatures are of this signal or of this particular type here. And these systems here, these mergers here, are taking place inside the cluster again and again and again. And we can think about these interaction trees that you basically have. So you form the binaries at what we call the hard binary limit. It keeps interacting with binaries as they're coming in here. And if it doesn't merge inside the cluster, it will be kicked out by the three-body recoil here out of the cluster, at which it might be able to merge within a Hubble time. It could also merge in between your scatterings. That's what you have here. So if you perturb the centricity to be large enough for the binary to merge in between your scatterings, it will correspond to, it will show like a eccentric laser source, but it could also merge doing one of the scatterings that I was showing. And this is really playing a key role in determining not only the eccentric population, but also the population of hierarchical mergers that has been very much into the literature recently, right? So Kende Hodakesega and I were writing out a paper here a couple of years ago where we were thinking about how to populate these mass gaps that people are starting to see being populated now. And the whole process is basically you're starting out with the 1G, or the first generation population of objects inside your cluster here. They start to undergo scatterings that I was talking about here. And these probabilities here are not small like the probabilities I talked about earlier. Basically, half of all the binary black holes in normal global clusters are merging inside the cluster versus the one that are being kicked out or merged outside. Right? And the one that are merging inside the cluster have the potential of pairing up with something again. And we can do this calculation here. We can follow all these trees and we can calculate the cross-section for all this to happen, basically with pen and paper. And we can do a different explanation or explanations of how binary black holes with different masses might be able to build up at least to second generation and keep on merging. And this here is showing like one of the spaces that we looked at here, where you have the velocity dispersion of your cluster and the central density of your cluster locked to that one. And you have different regions here. So in the gray region here, the binary black hole is not able to undergo a full scattering sequence before it's being kicked out, just because that it takes too long time. Okay. So the red one here shows it will always merge inside the cluster, and the masses here are 30 solar masses. And this one here shows where it's being. Let me see here. No, it will be ejected and merge outside of the cluster. Right? So depending on the velocity dispersion, the central densities, you can easily have systems where at least you have a mix of objects that are merging inside the cluster and then can undergo these hierarchical mergers here. And if you look at the different kind of mergers, the one that are merging inside the cluster, doing the triple scatterings, those are what we call the three-body mergers, and plot what is their peak frequency here, evolution as a function of time. You can see many of them will enter the LIGO band as they're still turning around. That means that they have not completely circularized yet. Where the one that are forming here doing that, or while the binary is sitting and waiting for the next interacting inside the cluster, called the two-body mergers here, they will come in here and being eccentric laser sources. So by a combination of eccentricity and how they move through the peak frequency space, then you can really take a spectrogram of exactly what is happening inside these clusters here. And this is here a snapshot of one of the cluster simulations that Kyle and Carl has been doing. And it basically shows the same here. You see the different populations of mergers that are coming into the different bands here. And it's really not that difficult to understand how or why they're separating out. It's all due to characteristic timescales, right? So if I take a binary black hole and tell me, or with a characteristic distance that you have inside a cluster, and say, well, this one here have to merge doing a triple scattering. The characteristic time for a triple scattering is about a year, and I put in here what should the periston, the distance, be between my two binaries, or what should the eccentricity be for that one to merge within this characteristic time scale, a year, doing my triple scattering. That would be my three-body mergers. Or I can just put it in here, the characteristic length scale, the masses, and the characteristic time scale here. I can get a peak frequency out at which they form, and they will form very close to the LIGO band. I can do the same exercise with the binary black holes that are merging in between my scatterings. Here the characteristic time scale is 1 over the interaction time, or 1 over the interaction rate, which is about 1 million years. I can put that in, and then you have to start to separate out all the different mergers in this peak frequency and the eccentricity space. You can do this for any kind of system where you have a characteristic time scale. Now, this was promising a few years ago in terms of figuring out where and how do binary black holes merge, because we're saying, well, we can calculate the exact cross-sections and probabilities for how these binary black holes are merging, and many of them will show eccentricity even when they come into the LIGO panel. A lot of people have been working on that recently. And we calculate about 5 to 10% of the binary black hole mergers will actually appear with non-zero eccentricity inside the LIGO panel. We did both pen and paper, we did cluster simulation. I think everybody agrees on this results now. But now a lot of other channels, of course, popped out that also can generate these highly centric mergers. Just one of the cases here that's been really discussed in the literature right now is the interaction of binary black holes pairing up in these AGN disk channels, right? So you have a supermassive black hole, you have a massive gaseous disk. The gaseous disk are able to capture these black holes, and then while they're inside the disk, they migrate at different speeds, and that depends on the mass. So if you have a mass spectrum of objects, their orbits start to overlap. You can pair them up and so forth. Right, and this is like a picture of some of the things that might happen inside these here. And if you just work out the timescales, and if you assume that you're pairing up objects and they're inside the disk, depending on how fast they're migrating and so forth, you will also find that binaries and singular are encountered in each other. And we had an earlier study trying to understand what is the outcome of these binaries as they're scattering off other objects inside the disk here. And we did this as a function of the inclination angle of my scattering, of my binary relative to the signal that is coming in. So if you're doing just the isotropic cluster case here, we have a binary scattering other objects here. That is what we call the 3D, the three-dimensional limit, where you have a binary, and the third object is isotropically being scattered off the binary. This is, the classical case here. You'll find the probability of a highly centric merger for one of these scatterings to be 10 to the minus, about 3. But if we now start to just push it down into a plane configuration, that probability raises by 2 orders of magnitude. And if you just follow binary black holes inside a disk, and you assume it's a planar geometry, like a 2D geometry, you'll quickly find that all of the binary black holes you have in the disk will merge on highly centric orbits, right? And if you then fold with the probability of this to happen here, you will can very easily argue, well, maybe like many of the binary black holes that we expect to see to be highly centric are formed in these disks here. This is not only true for binary single interactions. If you're just doing single captures, you find the same results. And it's all going back to this, the probability in the 2D case, the probability of R less than some distance, in counter distance less than some distance goes to square root R instead of just R. So we have many different systems that might create these highly centric mergers. So it is not like a stamp of a global or cluster slinger like anymore. So how do we disentangle all these different channels, right? So I want you to go in and look at this curvature. So this is the key. So if you, for example, have highly centric mergers forming through single captures in galactic nuclei, there will be nothing around. Okay, there might be a supermassive black hole, but it has to be really close. Trebles, you have the third object very, very far away, but these treble mergers that I showed you here in the clusters, let's take a further look at this. So you see this curvature here. Can we measure this curvature? And we can, and it's actually what I pointed out in the beginning here. If you have the scatterings here and you put an observer out here, you see that the binary black hole and these triple scatterings merge while they're still bound to the third object. And down here as an observer, you see this is time-changing time, like a retarded time that's changing as a function of time. And you can define this, either a form of just, time-changing time delay or as a phase shift. There's nothing weird in this. People have been doing this for binary pulsars for decades. If you're looking at the pulsar modulation, you will be able to infer all the properties of these systems, right? So you can do the exact same with gravitational waves. Now we're using the gravitational wave as your pulsar signal, and you are, under the assumption that GI is right, I can map out exactly what is going on around the binary, and I will show you a few examples of this. So we have this code here where we simulate binaries forward in time. That's what you see here. It's merging here, and at some point when it's merging here, I can take out the signal that we would get, and then I can make a reference signal by just moving, take out the third object. Here is a third object, and I can take it out if I have gaseous effects and everything. I just can take it out, then simulate my system backwards with my post-Newtonian equations here, and then I have a reference binary, completely clean reference, and I also have this perturbed one. So these are the post-Newtonian equations we're using in this work here. And then I can, for example, here I can pull out what is the frequency as a function of time as it builds up towards merger. The one that is very close to the supermassive or larger black hole here, you see you have oscillations in your gravitational wave signal here. And that is coming from tidal couplings of my binary with the massive black hole here. And the orange one is the unperturbed one. And you also build up these time lags or the phase shifts inside your signal. Okay. I did want to point out that many of these mergers, they will be eccentric as they're moving around your companion. So what is the effect of this? So eccentricity will actually add, like you can actually have much higher phase shift if you have eccentricity. And the reason is, so many people have been working on this phase shift here for the circular binaries, the line of sight acceleration. But if you have just a tiny eccentricity, you have much larger effects. And there are two effects. First of all, you have like a much more localized peak in your gravitational wave signal. So your signal is not blurred over, the entire period of your binary. It's more localized around the periods in the passage. So you have a much finer, time resolution from that. And you have another effect, and that is that the binary is going to enter the observable band slightly earlier than a corresponding binary with a circular frequency at the same frequency that you would have, so for example, for a highly eccentric binary. So you get many more cycles. Right? And that effect is basically, like you can take all the effects that people have been looking at so far for the circular binaries and just multiply it by a factor of the peak harmonic. So the peak harmonic has something to do with where most of the power is radiated, and if that is at factor of 10 or 100, you can take those phase shift measurements and multiply it by that peak harmonic, and that will basically tell you how large that phase shift is. And we did scatterings of this one here. So this here is showing one of the scatterings that we're considering in these clusters, and we did the analysis. We were doing millions of these scatterings here and calculated what would the phase shift be. This whole complicated system here can be mapped into what I showed here of a binary that is merging around a bound companion here. And we run it through our pipeline. And this here is a distribution of all the phase shift that we would get from a large example of clusters. And of course, our approximation is breaking at some point because some of the phase shift becomes extremely large. Order of unity of way beyond that. And that is because that doing these chaotic triple scatterings here, just by chance, the third object happens to be close by the binary as it's merging. Right? And we can calculate cross-sections. We can do millions of these scatterings, and very often we see that the third black hole is coming in and interrupting the binary as it's trying to spiral in. And all of these effects here will basically show up into your gravitational wave signal. And this is not a fine-tuned process, it's just a matter of statistical processes in the same way as you have some of them being highly eccentric. Some of them will just have a third object just happens to be very close. So for the binary black holes, we did that for the HN case. So we have a new paper out coming this week here where we take all the binary black holes that we could imagine could form in these HN disks and taking into account how close they form to the binary to the supermassive black hole, what the accelerations might be, and what the effect from the third object will be in all these scatterings here. And we found that a large fraction, so here are different evolution tracks of our binaries inside these HN disks. They of course, and the y-axis here is the phase shift. You see relatively large phase shift as a function of frequency. LVK is right here, so it might be able to probe the yellow population, which are the ones that are merging, doing a triple scattering where the third object is close by. What we didn't take into account is gaseous effect. But Conor Rowan, one of our new postdocs, he did simulations, the first simulations of 3 bodies with the gaseous effects. And what you basically find is that when you have triple scatterings inside these disks here, the energy transported or going through from the scattering towards the gas here compresses the system by orders of magnitude. And when you do this, this is a highlight of the normal gas friction model that people would use, the normal Oesterreicher drag. It doesn't capture any of these here, so you really have to do the full hydro. What actually happens is that you form binary or triple systems that are extremely compact. And when you have something that's extremely compact, it will show up with exceptionally high phase shifts. Right? So on top of having a lot of these triple scatterings and binary assembly, or binary assembly in these AGN disks, the gas hardening that we are now finding in the scatterings also lead to exceptionally high phase shift just because the binaries and triples are being, dragged to very, very small different distances. So on that note, I think here, let me see here. So there are other effects from gas here. I'm going to finish this here. And my PhD student Gaia, she just finished up a paper now on how the gas alignment inside the disk can also play a role, right? Because if you have highly centric mergers, they're also likely to be tilted or tilted around inside the disk, and the gaseous effect not only tend to shrink the orbits but also tend to realign. So there could be indications of chi-effective and eccentricity correlations. So I will stop there, and if you have some questions about how to break the mass and aren't degeneracy, I'm happy to talk about it, because all the line of sight accelerations, as I talked about, will only give us the acceleration. You really have no idea if it's a supermassive black hole or stellar mass black hole. But you can do it through strong lensing. So if you want to know something about it, this is your time to ask about it. Okay, thank you.
Thank you, Johan. We have plenty of time for questions. I will start over here.
Hi, Johan. I'm Yishan from Princeton, and I have two questions on the AGN channel. One very quick one. Do their eccentricities get damped by type 1 migration torques and circumbinary torques?
No, definitely, right? So if there has been a lot of work on how the eccentricity might even get pumped from gas drag forces, right? Okay. But then you really have to go into the Oesterreicher regime, where you assume like a uniform density, and the general statement is general result is that if you're losing most of your energy at upper center, then you tend to pump the eccentricity. Whereas if you're losing most of the energy at pericenter, then you tend to damp the eccentricity. And
that's seen in some of your simulations?
Well, so we are not able to follow the binary black holes all the way down to merger, but clearly we do see that there is damping. But many of the mergers that I was talking about that actually shows up a high eccentricity are not the binaries that are starting with relatively high eccentricity at lower frequency that slowly evolves. They're almost like plunging orbits, right? So the things that are almost forming inside.
They cannot be damped by the usual.
So it's very difficult to damp it. Yeah.
Dynamical friction torques.
So in terms of the Oesterreicher drag, right? So it depends very much on if the binary is supersonic or subsonic, especially at the upper center, right?
Okay.
But we clearly see here if we are putting in, so we also updated our code with having the gaseous drag forces, the Oesterreicher drag in all of these simulations here, and we essentially didn't find anything that was anywhere close to what you find from the. And there's a good reason for that, because. Well, very, very close. So Oesterreicher drag goes down exponentially as we go to supersonic via velocities, right? But here the scatterings that we are looking at here is basically mass that you are sloshing around, right? And it is not just the wake that we are looking at from the.
And the second comment is maybe more like open-ended. If you look at these waveforms in the LISA band when they are before merger. Maybe the phase shift will themselves have some periodicity, right? The phase shift actually goes back twice in Emery, phase. So then that will be indicative of the system.
Yeah, that is absolutely right. But many of the systems that we're actually seeing that are forming close to something else will never show up in the LISA band.
Oh.
Right, so if you need to have something that is forming close to something else, you basically need it to merge and being assembled on a very strong dynamical capture. Otherwise, there's no way that the third object could have been there without tidally.
So their frequencies are still very different from usual Emery.
They're very, very different. Yeah. Okay. So basically, none of these systems here will show up in the LISA band. Yeah.
I see.
So these are like prime targets for 3G and also for, of course, the cycle. But I don't know if you will be able to see them. Yeah.
Thanks. Very exciting talk. Lots of questions. The first thing is that you say you're going up to post-Newtonian 2.5.
Yeah.
That's the first order in which you get gravitational radiation, but it's generally the case that it's non-monotonic as you go up to even higher orders. Are you worried?
It doesn't converge.
It doesn't converge
right,
very
so
well.
That's the problem. Yeah, exactly. Yeah.
Do you have some idea about how that might change the statistics of what you're seeing?
Well, there is certainly one thing that that is changing to leading order, and that's our definition of eccentricity. So when I'm going in to calculate what is eccentricity at 10 hertz, I just take the Newtonian elements and just calculate what is the eccentricity. But when you have these strongly precessing orbits, I cannot even define eccentricity in the usual manner, right? So if I'm actually going, well, you might laugh, but there's a lot of people here that's working on exactly what the difference is.
I just like to laugh. Don't worry.
Yeah. So maybe within an order of 1 to 2, maybe you can get a different fraction compared to how you define it. But there is. It is of course true that if I have very, very close encounters, I might have a small mismatch. Yeah, and there might be some ways that you can mix the EOB models with what I have here by doing some kind of splitting. We are looking at that right now.
And I want to ask just one other question very quickly. I asked this earlier in the week. When you have a merging binary system that has an eccentricity, you normally would think that in an isolated context, if it had an eccentricity, that would damp away, particularly if it had a long time to actually circularize. So do you get a sense of the distribution function of the birth times from the eccentricities you might see at merger? If it's still eccentric at merger, then it likely was formed fairly early.
Okay, that's a very good point. So the problem that we normally have is that when we look at globular clusters or any system, then you have the time delay, and that is going as 1/t or something, and that time is usually comparable with the Hubble time. So when we see all the mergers, we have no idea if it was a binary black hole that formed a Gierke years ago or 12 Gierke years ago. But the eccentric ones are timestamps of exactly what is happening inside the cluster of the systems at that time that you observe it.
Yeah, that's why I asked the question. I'd like to see what that distribution. We can talk offline.
No, that is absolutely right. So Mike Savin and I and Isabel has been thinking about this. So, but you're absolutely right.
Thanks, great talk. I probably have a very naive question, but I guess for this to work, you have to be in a very eccentric orbit, and the effect of this shifted gravitational waves only going to happen if you're very close to the pericenter of the outer orbit. Yeah, and that is a very short time compared to like the whole orbit, right? So, with, let's say with 100 models, with 100 LIGO events, assuming that they're all like doing this, then there's a duty cycle that you can observe this. Do you actually expect them to see them with? I hope I phrased my question.
Okay, that's a very good point. So all of the scatterings that I showed here, of course, take into account that there is a distribution of it is much smaller probability that it's going to be through at like a.
You have to be lucky to be. You
have to be lucky, yeah.
You have to how be lucky you have to be, like, for example.
Well, so right now we have not calculated that exact probability yet. But calculating the cross-section for this to happen is the same with the eccentric. You're absolutely right. This will be the next step.
Okay, thanks.
Yeah, no, but that's a very good point.
All right.
I think the point is that we see that they're forming, right? So if you observe a few hundred, or of order 10, like eccentric mergers, you will start to expect to see one of these.
As a reminder, please say who you are before you ask your question.
Oh, that's a great reminder. Hi, John. I'm Salvo Vitale, MIT. Yeah, so we had some discussion in the previous 2 days about eccentricity and parameter estimation.
Yeah.
So for the results you showed earlier, I guess I'm on the skeptical side, right? Because one thing that often it's done is that those results are obtained using a flat prior on the eccentricity, right? But your work and Carl works and Kyle and others show that the expected distribution of eccentricity peaks very strongly at 0, even in dynamical environments, and there is a tail, of course, at eccentricity. So why isn't that a better prior to use? Like, it seems like a bit circular to use a flat prior, get an eccentric result, and then use that to justify why we're excited about eccentricity, right?
That is right. Like honestly, I have not gone too much into how that propagates to these results, like in terms of what
right. For example, for the latest one of the NSBHs that are being claimed to be eccentric, right? People at Rochester have rerun those with different waveform and a uniform in log prior as opposed to a uniform prior, and they get it is consistent with 0. It can still be large, but it's not inconsistent with being circular anymore. And so I guess this is to say that measurement of eccentricity with LIGO, Virgo, Kagra data is still delicate enough that at least I'm typically cautious and present those results as it's not inconsistent with, as opposed to it's definitely a detection for. That may just be me though. My personal thing is also that the gravitational waveforms that we actually have to fit for the eccentricity are just not good enough, and especially also when you think about the spin. Like so many of the one here, you assume like a line spins, and we already know that the things start to mix the spin orientation and the eccentricity. I think the way I'm thinking about this, if nobody is pushing along this one here, trying to make progress in this, then maybe it's more difficult than people thought. I'm not entirely sure, but I think a lot of things are happening during these years. Yeah.
Thanks for a nice talk. I'm Sukanya Chakrabarty. I wanted to ask about the line of sight accelerations. Now, maybe I missed it, but for binary pulsars, the way that's usually determined is you need very, very precise measurements over about a decade or so. And so in this case, with the supermassive black hole, is that the case, that you really have such a long...
No, we are talking seconds or minutes.
Right. So how is it working for you?
It's working pretty well. Okay. One of the problems, like people have been, thinking similar thoughts for different systems, but the thing is that maybe this will answer a little bit. The thing is that here I'm keeping track of the phase of my gravitational wave signal. So it is not like the pulses that I'm trying to see, like is each pulse, redshifted, has it been, widened or things like this. But if you have access to the phase of your signal, then you can do these things here much more accurate, right? So the time delay here that I'm talking about, could be like a fraction of a second between like the curved orbit and the unperturbed orbit. And when you're going back, even for binary neutron stars and even for binary black holes, when you just calculate the orbital, like accumulated orbital phase, for some of these systems, you can easily reach order unity. But these figures that I showed here was for frequency of 5 Hertz, right? And the phase shift goes as f to the minus 13/3 that you can calculate. So it's very, very sensitive to the frequency that you are looking at. On the other hand, all those estimates would only be for circular binaries. When I'm arguing that if you have eccentric binaries, essentially each frequency or each harmonic that you're looking at has a much, much smaller wavelength, so you can do much more precise measurements. It is a straightforward calculation, and it seems to be extremely promising.
Yeah. Hi, Daniel Holtz, Chicago. Beautiful talk. 2 questions. One is just I'd love to hear more about the strong lensing, breaking the degeneracy.
You were very critical when we made the section. I really wanted to hear your, but doing long so we can talk.
Great. Yeah, so we'll talk about that. And then the other thing was, given all the excitement about the 2G, 1G population, kind of channeling salvo, if we're not buying any eccentricity so far in the population, at what point does having no eccentricity in the population, given kind of the way the models are going, at what point does that become problematic for all these different models?
I would always say 1 in 100. If we don't see something like 1 in 100, maybe then the cluster channel is suppressed at least by even like an order of, maybe not an order of magnitude, but maybe 1 in 5 or something compared to other channels. Yeah. Maybe I just want to, Carl, just 30 seconds. Oh, okay, yeah.
You have exactly 30 seconds.
What I wanted to talk with people about here, if they, and especially also what Daniel was talking about, is that if you have no idea what is going on here with the strong lensing, it provides you with 2 different sidelines towards the source, right? And we are putting out a new paper this week on that as well. And when you have combining the the information from the different images that you see in strong lensing, you can see that you can triangulate for exactly what the source is doing because you have a baseline that is basically the Einstein angle times distance here. Right? Doesn't matter. You just want to make sure that you see both images before your operation runs out.
That's why.
Yeah, exactly.
All right, let's thank Johan again.